The answers to both sets of homework that we had over the weekend are up on the board. Have a look at the answers to worksheet 14 and 15, and let me know if you need any of these questions gone over. Patrick? 14, 1 and 2. 15, number 1. Okay. Curtis? 15, number 5. Okay, I expected that one. Okay. So Michelson seems to be a bit of an issue for us. It's good that we have this worksheet. It's good that you're asking me to go over these questions because we are having a quiz on Michelson tomorrow. So let's go over all 3 of these. Let's make sure that we're in good shape with this. Let's have our quiz tomorrow, and then we'll go from there. Question number 1 on worksheet number 14 says, the speed of light found by a Michelson experiment was found to be 2.90 times 10 to the 8 meters per second. If the 2 hills were 20 kilometers apart, what was the frequency of the rotating mirror? Speed, obviously, we can write down as 2.90 times 10 to the 8 meters per second. The distance is what? We're given 20 kilometers here. The temptation is just to write that distance down as our distance, right? We see a number that has the kilometers, meters, whatever, and we think, oh, okay, that's a distance. That's what we got to use. But it's not in this case. Okay, the distance from one hill to the other is 20 kilometers. Therefore, the distance the light travels from the rotating mirror to the plane mirror back to the rotating mirror is going to be 40 kilometers. We got to remember to convert that to meters as well. So let's make it right now 40,000 meters. We're looking for the frequency of the rotating mirror. Remember that when you're solving these problems involving Michelson's experiment, including on the quiz tomorrow, the one single question on the quiz tomorrow, you got to always use the same 2 equations, always. Those 2 equations are, what's one of them? Somebody tell me what one of them is. T equals 1 over F. Good. Doesn't matter what order you put them in. I always put that one second, but it doesn't really matter. What's the other one? Good. V equals D over T. Always. Again, it doesn't matter what order you put them in, but you got to use both of these equations. Now, tell me what little t stands for. We got little t, we got big T, 2 different t's, right? 2 different times. What does a little t stand for? Time, but specifically what time? Good, good. The time for 1/8 of a rotation. And big T stands for the time for 1 complete rotation, 1 complete revolution. So sometimes we put a little subscript there to remind us of that, but if you remember that, that's fine. You don't need to put that subscript in there. Let's plug in some numbers here, see what happens. If I had to bet, if I had to put money on this, I would bet that we're going to end up solving for a time. Okay, and I would bet that it's going to be not the time that we actually want to use in the equation that we use to solve for what we're looking for, the frequency. Okay, we're going to need big T to solve for frequency. My guess is that we're going to get little t out of this, and then we're going to have to convert that. We'll worry about that when we get there, though. V is 2.90 times 10 to the 8 meters per second. The distance is 40,000 meters. T, little t, we can find here. 40,000 divided by 2.90 times 10 to the 8. I don't actually have the answer on my sheet for that. What is that? 1 point times 10 to the 1.38 times 10 to the negative 4 seconds for little t, the time for 1/8 of a revolution. Now, we want big T. Remember what we said? We always, when we get a time, it's never the time we want. We always have to do something with it to get the other time. What do we got to do here? Multiply or divide by 8? We're going to multiply because the time for 1/8 is, of course, going to be 1/8 of the time for 1. So let's multiply that by 8. What do we get then? 1.38 times 10 to the negative 4 times 8 is? What is it? Times 10 to the negative 3. Now let's plug that in here. 1.10 times 10 to the negative 3 seconds equals 1 over F. And take the F up, the 1.10 down, and we end up getting 906 hertz. Now, most times we do a Michelson problem, the frequency of the rotating mirror is going to be somewhere in that 500 to 600 hertz range. Anybody suggest to me in this case why it wasn't in that normal range? It doesn't mean we're wrong when we get something outside of that range. It's just that I'd say half the time or more, we're going to end up with 500 to 600 hertz. Why didn't I get that range here? Holly? Not so much the speed. Okay, I did use a different speed, slightly different than the accepted value, but it's not all that much different. It's about less than 1%. Yeah, usually our distance is quite a bit more. Right? So think about it this way. If the light if the light is traveling not much more than half as far, it's going to do it quicker. If it's going to do it quicker, then in order to go 1/8 of revolution, the mirror has to be spinning faster, right? In order to make 1/8 of revolution in that same amount of time. Okay, so if we get a smaller distance, we're going to get a bigger frequency. It's not going to be in that 500 to 600 range. Okay, let's take a look at number 2 here now. This one says Michelson used an 8-sided mirror to measure the speed of light. The mirror was rotating at 1.87 times 10 to the 6 revolutions per hour, and the two hills are 35 kilometers apart. What did Michelson determine the speed of light to be? We've got a frequency here. It's 1.87 times 10 to the 6 RPH, revolutions per hour, which I'm going to, since I can't circle it in my question, since I don't have my question written down there on the page, I'll just circle it right there to remind me that I want to convert that to revolutions per second, hertz, right? I'll worry about doing that in a minute here. We've got a distance here. It says the two hills are 35 kilometers apart. We know right away that we're going to double that distance, and we're going to convert it to meters. So let's just make it right now 70,000 meters. Now, that's a pretty typical distance. If it's a pretty typical distance, then the frequency is probably going to be in that 500 to 600 hertz range, right? Clearly, we're not 500 to 600 right there. So that's telling us that it's another reminder that we're not in the right units here. How are you going to get that in revolutions per second? How are you going to get that in hertz? You're going to multiply or divide. Bless you. You're going to multiply or divide. Bless you. Yep. We're going to divide, yeah. If we divide by 60 and then 60 again, that's the same as dividing by 3600, then we're going to get the number of revolutions per second. Now, some people try to multiply on this one, right? Say, oh, okay, there's 3600 seconds in an hour. Let's multiply. But think about what you're doing there. Okay, if you multiply by 3600, you're going to get a number that's bigger than what we have here. If you have this many revolutions in an hour, you're not going to get more revolutions in a second than you get in an hour. You're going to get less. So it's going to have to be divided. Divide that by 3600, what do we end up getting? I'm going to guess 550 hertz. 520 hertz? Is that exact, Bryson? Okay, 519.45 hertz. Let's go with the unrounded number, because it's not a final answer, right? So we're solving for speed. We know we're going to write down those two equations again. What was one of the equations, Nick? Good. What was the other equation that we had there, Curtis? Good. Big T is equal to 1 over F. Good. Little t, time for 1/8. Big T, the time for 1 complete revolution. Plug in some numbers here. 70,000 meters divided by little t. We don't know what it is. Big T is 1 over 519.45. Anybody have a value for big T there? .925 times 10 to the minus 3 seconds. Now, how are we going to get that? How are we going to convert that to little t, the time for 1/8 of revolution? We're going to divide it by 8, right? So little t, the time for 1/8, is going to be what? 2.406 times 10 to the minus 4. And when we do the calculation there, it works out to be 2.91 times 10 to the 8. Listen, if you're solving for speed, and you get a speed that's that close to the speed of light, 2.91 times 10 to the 8, you're probably right. No guarantees, but you're probably right. If you're wrong on it, you're probably going to get a number that's either the wrong exponent, which is a big flag right there. You got to recheck that. Or even if you get something like, half of that, 1.45 times 10 to the 8. It's possible. Either you could get that because, experimental data can provide you with sometimes results that aren't what you expect. But it's not likely. So you're usually going to get somewhere in that range for speed. And finally, question number 3 on worksheet number 14. It says, what's the frequency of rotation of a 6-sided mirror if it's used in a Michelson experiment if the hills are 30 kilometers apart and the speed of light is 3.1 times 10 to the 8? So we got a speed of light that's slightly off at the accepted value. We got distances that are off of the norm of 35 kilometers there and 35 kilometers back. What do we expect to get for frequency here? I wouldn't expect our frequency to be crazy off of that 500 to 600 hertz range, but because we're off in both our speed and our distance off of the norm, we could be out of that range a little bit here. Let's write down our givens again. We got a speed this time of 3.10 times 10 to the 8 meters per second. We got a distance of 60,000 meters, and we're looking for the frequency. My two equations, V equals d over t, and t is equal to 1 over f. Plug some numbers in. .1 times 10 to the 8 equals 60,000 divided by t. Anybody have that? Little t? 1.86 times 10 to the what? 13? I don't think so. 1.935 times 10 to the 4. You know what, Rob, I'm glad that you got that number. I don't know where it came from, whether you multiplied them or what, but I'm glad that you got that number. I think you did multiply them, actually. But here's why. Okay. What was the number you got there, 10 to the 13? Okay. So Rob gets a number that's 10 to the 13 for seconds. Okay. Let's just stop and think about that for a second. 10 to the 13 seconds. We're saying that light travels 60 kilometers. Is it going to take 10 to the 13 seconds? That's a lot of seconds, right? That's a lot of seconds. Light's going to travel that far, 60 kilometers, in almost no time, right? So there's a red flag right there that number just doesn't make sense. Okay? I didn't know what the number was supposed to be, Rob, when you gave it to me. I just heard that exponent and thought, that doesn't make sense, right? That's where I want you guys to be as well. Right? You get a number, everyone's going to make those mistakes. Everybody is. But I want you to spot that as being an unrealistic number when you do make a mistake. All right, so we got this number. What do we do with that to get big T now? Because remember, it's not the time we want. We're going to multiply it by 8. When we do that, we get big T. What's its value? It's a 6-sided mirror, isn't it? Yeah, be careful with that, okay? Hey, again, we couldn't circle that on our sheet here, but or on the board here, because this question's not on the board. But when you see that on your sheet, as soon as you see that word 6, circle it, because that's not normal. Right? We usually use an 8-sided mirror. So if you see something other than the norm, okay, that's what leads us to silly mistakes like the one I just made until you guys corrected me. Multiply it by 6. That gives us big T. Time for 1 revolution. What do we get there? 1.16 times 10 to the negative 3. And then we solve for frequency, and it works out to be 861. What did we predict? Oh, we said it could be outside of that 500 to 600 range a little bit because our speed was off and our distance was off a bit. But it's reasonably close, right? Okay, we predicted that it would be close, but off a bit. What is it? Fairly close, but off a bit. So odds are you get a number that looks like this, and you're fairly confident that it's right. You think, should the frequency be higher? Yeah, it should. Light has to travel not as far, so it's going to do it quicker. And according to this, it's traveling faster, so it's got to do it quicker again. To make 1/6 of a revolution, it's going to have to do it in a quicker amount of time. Plus, it's a 6-sided mirror as opposed to an 8-sided mirror, right? So it's going to have to do it all quicker than it would under the normal conditions. How do you guys feel about those 3 questions? Comfortable? We get a quiz tomorrow, 1 question, just like, no harder than what you've seen up on the board here today. Get 100 on it? Good. Good. No tricks, just simple. I might give you a, revolutions per hour or something like that. No tricks beyond the difficulty that you've seen here today, though. You want to be in revolutions per second, yeah. Yeah, Hertz is revolutions per second. Okay, worksheet number 15 now. We only had one of those questions, I believe, that we needed to go over. That was question number 5. This one, honestly, isn't as hard as it seems. Let me read this one, and then we'll kind of draw a picture of it and show you that, hey, really, it's easier than it might seem. A radio wave with a frequency of 3.0 times 10 to the 8 hertz travels from ground level, a distance of 50 meters, reflects off a metal roof at an angle of 30 degrees, and then returns to ground level. How long does it take, and what's the wavelength of the radio wave? So here's ground level. Here's the roof. The radio wave with a frequency of 3.00 times 10 to the 8 hertz is coming up here, striking the roof, and then bouncing off at an angle of 30 degrees. Okay, we know that it's got to be going up at an angle of 30 degrees as well if it bounces off at 30 degrees. Go ahead.
I did not draw it like that, but I got it right.
How'd you draw it?
I draw it like an angle piece of metal.
Yeah.
Yeah, and I just had to hit it.
Yeah.
Bounced off.
Yeah, somebody in my morning class said the same thing. The wording of the question wasn't great, and I told them that it's, you know, as difficult sometimes as the diploma exam is, as challenging of a question as they'll give us sometimes, the question isn't challenging because it's not clear what they mean there. So this is a little unclear, this question. Okay, I think if you got this question on an exam, they would word it better than I have, or they would give you a picture to show you. So don't, is that right? Okay. So don't panic. Don't panic about how you've drawn it. As long as your solution is consistent with how you've drawn it, then that's good enough. Okay? On an exam or on a test, you should expect to see either a diagram or better wording for it. This is the way we're going to solve it. But again, if you've interpreted the wording a little bit differently, I can understand that. This distance right here, they tell us, is, or I tell you, is 50 meters. And I think that's all we have. We're looking for t, and we're looking for a wavelength. Okay, we can solve for little t here. We know that v is equal to d over t, and t is therefore equal to d over v. What distance does it travel? If it goes up there and then down here, the distance that it travels is what? 100 meters. And the speed is 3 times 10 to the 8 meters per second. So the time here is going to be, what is that, 3.33? I don't have that one on my sheet here. 3.33 times 10 to the minus 7. There's our time. Now, what relevance was the angle there? None. As long as we were told it's 50 meters there and 50 meters back, the angle was irrelevant. Now, that angle could become relevant if they wanted to make this question a little bit trickier. Maybe they don't give you that 50 meters right there. Maybe they scratch that out. Maybe they make this distance 80 meters. Okay, if they make that distance 80 meters, then all of a sudden that angle is important. Okay, then we have to figure out this distance. We do that by cutting that, saying that's 30, this is 60. Okay, 60, this is 40. We could solve for the hypotenuse right here and then double that to make it our distance. Okay, that's not what we were asked, but if we were, it would become a little bit trickier geometrically, but conceptually not all of that. If we want to solve for the wavelength, which we're asked to do here, we're going to use the wave equation that we learned in Physics 20. V equals F times lambda. Lambda is equal to V over F. And plug in our numbers here, 3 times 10 to the 8. Frequency happens to be 3 times 10 to the 8 as well, which makes the math really easy here. Lambda is equal to 1.00 meters. Now, Rob just pointed out to me that the answer that I had when I gave you the answers at the beginning here was 3.59 times 10 to the minus 7 for the time. That answer was consistent with going up, straight up, and then down at 30 degrees because maybe the roof was at an angle. Because if you drew it that way, then that's the answer you should get. If you drew it this way, then this is the answer that you should get. Good news. A little bit of homework for tonight. Please do the following for tonight, please. Page 652. I'd like you to do question 1 and 2. And 5 to 11 for homework tonight, please. The The bad news is you're not going to have any time to work on it right now. We're going to move on. Might have a little bit of time later on, but might not. 652, 125, 211. Today we're going to move on and talk about reflection. Over the next couple of weeks, we're going to talk about both reflection and refraction, the bouncing off of light off of a boundary, and the bending of light when it strikes a boundary. Okay, next few days is going to be reflection. Fundamentally, we have to know this basic law before we move on anywhere here. The law of reflection. We talked about this a little bit in Physics 20, but only briefly. It says the angle of incidence, as measured from the normal line, which you might not remember what that is right now, is going to always be equal to the angle of reflection as, again, measured from the normal line. In physics, normal means 90 degrees. Physics 20, we talked a lot about the normal force, the force that the ground acts or pushes up with. Well, that normal force always pushed up at 90 degrees. If you're on a flat horizontal surface, the normal force was straight up. If you're on a hill, then the normal force was not straight up because 90 degrees to the hill isn't straight up. Normal means 90 degrees. So if we're measuring the angle of incidence from a normal line, then we're measuring an angle of incidence from a line that's drawn 90 degrees to the boundary. 90 degrees to whatever the reflecting surface is. Now, the angle of incidence is going to be that angle that strikes the boundary, or it's going to be that ray of light, I should say, that strikes the boundary. But we're going to measure that angle of incidence from that normal line that's 90 degrees to the surface. It's going to bounce off like this. We're once again going to measure the angle, this time theta r, from the normal line, the one that's 90 degrees to the surface. The law of reflection says that theta I, the angle of incidence as measured from the normal line, equals theta r, the angle of reflection as measured from the normal line. That law holds every single time. There are times when it appears to not hold. There are times when a ray of light maybe strikes a boundary like this and then bounces off like this. Well, that certainly doesn't appear as if the angle of incidence equals the angle of reflection. But if you look closely, if you look microscopically at the surface, then the surface can be rough. If it's rough, then the angle of incidence will still equal the angle of reflection, but it will equal it at the exact point of contact of the light with the boundary. Does that make sense? So if you got a rough surface, basically what we're saying here is that that surface right at that exact spot may actually look like this, and you just don't notice that. If we look at that closely, you can see that the angle of incidence still roughly equals the angle of reflection there from that microscopic spot on that surface. It always holds. If you get a plain, perfectly smooth surface, we call it specular reflection. All the rays come off at the same angle that it struck it at. If we've got a rough surface, we call it diffuse reflection. It still obeys the law of reflection, but the rays go off in every direction possible because the surface is rough and the surface has different angles. Always holds, though. Any way you look at it, it always holds. Got a couple quick little examples for you here. The first one's pretty easy. The second one, a little bit tougher. We got a ray of light striking a boundary up here in the first one at 48 degrees. What angle is it going to bounce off at? 48 degrees. Easy, right? Easy question. Second one, a little tougher. We got a 90-degree angle for these two mirrors here. We know it's going to hit the first mirror. It's going to bounce off the first mirror. It's going to strike the second mirror. It's going to bounce off the second mirror. The question here is, what's the angle that it bounces off the second mirror at? What's the angle of reflection off of the second mirror? What are you saying it is, Rob? 55? It's going to bounce off the first one at 55 for sure, right? If that's 55 degrees, then you can tell me what that angle of incidence is right there. It's going to be 35, actually, yeah. It's going to be 35 because if that's 55 and that's 90, and it's got to be, then that's got to be 180 minus 90 minus 55, right? All the angles inside the triangle have to work out to be, or add up to be, 180 degrees. So if the angle of incidence there, Rob, is 35, what's the angle of reflection going to be off that second mirror? No? 35 degrees. Okay. So the angle of reflection off of the first mirror, 55. Off of the second mirror, which was the question here, is only going to be 35 degrees. Now, don't panic about this writing. I'm not going to make you write all this stuff down. I'm going to summarize it for you here. Here we've got a setup of the first ray diagram that we're going to draw. The vertical line there with no arrow on the end of it represents a mirror. The vertical line with the arrow on the end of it represents an object. It could be you standing in front of a plain flat mirror, or it could be anything standing in front of a plain flat mirror. We just put the arrow on it to represent the top of the object. So the top of your head, or the top of my Slurpee cup, or the top of whatever, the top of whatever our object is. Let's say it's you. You're standing in front of a plain flat mirror like you do in the bathroom every morning. You see yourself in the mirror. What does that image look like? What are the characteristics of that image? Is it bigger? Is it smaller? Do you appear to be, like a funhouse mirror, really, really wide, or really, really skinny and tall? I mean, what are the characteristics of that image? You know from experience what you're going to look like when you look in that mirror. But if we had to predict it based on laws of physics, how would we do that? We're going to draw what we call a ray diagram. A ray diagram shows rays of light that reflect off of the object, or that come from the object, and then reflect off of the surface, like the mirror in this case. We're going to use those to determine where the image is going to be and what's it going to look like. There are millions of rays of light that are reflecting off of this object. You get up in the morning, you go to the bathroom, you flip on the lights, there's millions of rays of light reflecting off of all parts of your body. We're going to look at 4 of them here. Only 4, because that's enough to tell us what the image is going to look like. We could use the other 999,000, whatever, however many rays there are. We could use them all, but we don't need to. 4 is enough to tell us what the image is going to look like. We're going to pick the 4 that we use simply because it's easy to predict what happens to those rays, and therefore easy to predict what the image is going to look like. The first ray that we're going to pick is a ray of light that bounces off of or reflects off of the top of the object. So we've got a ray of light right here. Let's make that an arrow. We've got a ray of light right here that comes from the top of the object, strikes the mirror. Where's it going to bounce back? Where's it going to reflect? Directly back. Yeah, if it strikes the mirror straight on, it's going to reflect back straight on. So it's going to go back here. The second ray that we're going to look at is the ray that comes from the bottom of the object. Strikes the mirror. It's going to go straight back. 2 more. 2 more rays. 1 more ray is going to go off of the top of the object at an angle. So it's going to bounce. I'm going to use a different color for this one. It's going to come from the top of the object down to the mirror right there. It's going to bounce down here somewhere, such that the angle of incidence equals the angle of reflection. It's actually not going to be quite that big of an angle, I don't think. Let's make that a little bit smaller. More like this. The 4th ray that we're going to draw is another ray that comes from the bottom of the object, something like this. It's going to reflect something like that. We're almost there. Let's extend these rays now. Let's extend not the rays that struck the mirror, but the rays that reflected off of the mirror. The first ray that reflected off of the mirror went to the left, so let's extend that to the right. The second one reflected to the left, so let's extend that to the right. The third one reflected down this way, so let's extend it up this way. And the fourth one reflected up this way, so let's extend it down this way. Where these two dotted lines intersect, they came from the top of the object, so that's going to form the top of our image. And where these two rays intersect, they came from the bottom of the object, so that's going to form the bottom of our image. Our image is going to look like this. There are three characteristics of every image that we describe. The first one is based on the size. Doesn't really matter what order we do them in, actually, but we'll call that one our first one. Is it larger? Is it smaller? Or is it same size? Let's look at the object. Okay, let's look at the size of the object. Let's look at the size of the image. And I want you to tell me whether the image is bigger, smaller, or same size as the object is. What's the answer to that question? Same size. The image is the same size as the object is. We know that because, I mean, if we have to take a ruler, we can measure them both. We'll find it the same. When you look in a mirror in the bathroom,